try that? Yeah. Can we try? Okay. So yesterday we heard from Keysight about one of the tutorials about the overall things about the Keysights. Today, I think both Winston and Dan will go into a little bit more details onto this Chakra, which is the standardized AI workload traces they have been designing for co-designing. So with that, I think the introduction, I think the slides went away. Or can you? Yeah. So let me introduce both of them. Dan is a senior software architect at Keysight Technologies based in Bucharest, Romania, with extensive experience in building networking and security verification systems. Dan currently leads teams at Keysight Technologies, Romania, focused on developing AI infrastructure, emulation solutions, and drives collaboration with academia and industry partners. Winston, he's the chief architect of Keysight Technologies, leading the development of simulation and emulation solutions to evaluate the AI cluster infrastructure. And his extensive background includes cloud computing, network visibility, and creating network emulation and simulation testing systems. He has held key engineering leadership positions at Keysight, Axia, and Scheidas. And Winston holds the bachelor's and master's degree in computer science from UCLA. So let's welcome both of them, Dan and Winston, for this talk. And I think, Dan, you flew from Romania, right?
Yes.
Yeah, you flew from Romania over the weekend. So thanks. And again, Rakesh also has flown from India. So I think we have a lot of global presence, and we have three of them from South Korea visiting here. So, and Martin, of course, is from Germany, but he told them he has a temporary assignment in home in Chicago. So good. We have a lot of international presentations. So let's get started.
Yeah. Okay. Guys, hear me okay? I'm fine. Yeah, so we're pretty happy to be here. Like Dr. Panda inviting us, to visit the research group and the community here. So we're kind of lucky to be the last sort of external speakers, at the end of the day, because we're kind of standing on the shoulders of all the giants from yesterday and earlier in the morning. Kind of how it works, right, in systems. So our talk is gonna be a little bit higher level, meaning like we're gonna come from all the way at the top from the workload perspective, okay? And how do we actually think about maybe a standardized way to describe those workloads so that we could actually enable in general, right? How do we do system level code design and optimizations? So again, right, we're standing on the shoulders of the giants. We don't need to go through a lot of the stuff, but it's really about we're looking at system level code design, right? We're looking at really an iteration loop, right? You put certain systems together, you put it in production, whether it's HPC or AI workloads. You observe it, right? You take some instrumentation back, right? And then sometimes you hit bugs. You call the vendors. You work with your partners to debug the system, reproduce them, and then sometimes like you fix them, you put it right back into production. And sometimes you actually need some of these workloads that you have running today to design the next generation systems with all the new technologies come up. And you do a lot of that basically in simulations, right? And early prototyping with FPGAs, emulators to test those small components before everything then, sort of eventually form the overall system, right? The cluster. So really like, this loop, right, involves a lot of different personas, right, at different layer of the stack. And you look at the stack on the right, that's typically your AI, kind of stack, right, all the way from the top the models. Then you have all the parallelization strategies, like, talks that happen before, that happens in the training frameworks, the inference frameworks, right? And then you have different scheduling, communication policies, workload scheduling, and everything, CCLs, and all the way trickles down into all your hardware, firmware, and things like that. So really, then what's the challenge, right? Like, you look at that stack, right? There's so many different teams with expertise involved at different layers, right? I think just like, earlier, right? It's like the quantum talk. We don't want everybody to be a quantum physicist. Similarly here, right? Somebody maybe who's very familiar in networking at the lower layers. Do we really want to learn about everything about the shape of the model, learn how to use PyTorch and all this other thing, right? Very similar, right? So you get a lot of these like full workload benchmarks. Eventually people try to basically like run on the real systems, right? Involving a lot of these the real sort of production grade frameworks, run the workloads, but it works for the guy at the top, but doesn't necessarily work for all the people working in the lower layer of the stack, right? And I think another challenge is just that, you have a lot of different sort of ad hoc benchmarks, right? Everybody sort of then start designing sort of experiments specific to their domain or their layer. And what you end up doing is like, eventually when you need to actually turn up the whole system, right? And then evaluate sort of like how the end workloads that's going to run over the system is going to behave, they're all kind of talking different languages, right? You can't really take some experiments that you did at the low level, translate it directly to something higher layer that's meaningful for the guy at the top. So these are basically the, kind of like the challenges, right? That people face as you actually start designing new systems or even reason about, current systems that you're trying to maintain, debug, and operate. So now it's like, so what's the fix, right? So we think really the answer is, some standard way, right, to describe. In general, I would say, we're saying AI workloads, but in some ways, like all the workloads, if you think about it, right, it's really just a computational graph, right? And that has certain dependencies, right, on things that you compute, and then memory or data that you move to different parts, and then, communication that happens as you do the movement. So really, like, what is that common language, right? So you need a few things, right? With that common language, you need basically portability and replayability, right? That's the part I mentioned about, because there's so many people involved in the code design ecosystem, you want a common language so that experiments are portable, right? Reproducible across different domains. So that's one, right? And then the other one is like, ideally, right, this should be lightweight, and then we should make it, I would say, very vendor neutral, implementation neutral, in a way where, it's a common just language that any implementation could interpret and then act on it, right? And finally, is like anything you do here is like kind of, ideally, right, that format or schema should be representative and something you could extend, right, to not just cover AI workloads. It could be HPC workloads, or it could be some other workloads that has any type of these east-west complex dependencies. So, this is not a sort of, I think is like a problem that only us at Keysight could solve alone. We think it requires a community effort, right? So that's why sort of like we're doing this as part of this Chakra effort, as part of ML Commons. So very quickly, right? This is quite new, right? This community is only about, a little over 2 years old. And these are the people that, that are regularly involved having that same vision across all the different, some academic institutions and different companies across the system space, test and measurement, and other places. We're not quite there as this community where, you're able to do the great engineering work for 20 years. So you still see pictures up here, but, we're hoping, some point we could actually grow it to a point where there's a lot more contributors, and then, and also maybe we could work together, right, to advance the whole system space. So just a little bit on sort of like what this ecosystem is, right, that we're starting, so that we're, before I pass it on to Dan, right, to talk about all the details, really, like, if you think about it, right, the centerpiece of this whole Chakra ecosystem is really a schema, right, that basically gives you the language to describe workloads in terms of its data and control dependencies. So the idea is that, like, really that language allows you to capture the essential execution semantics of workloads, right? The compute, the memory, the communication operations, and really the dependencies of when they're executed, and the order, right? So basically, like, once you have the schema, right? Again, like earlier, we talked about that whole code design cycle where you go through the observations and all that stuff. So there would be tooling that allow you to, if you actually run PyTorch or some training framework, you'll be able to actually, emit traces in the format of, eventually turn into the format of this language, so that, downstream, there's open source tool that could actually, be used, right, to do replay on current physical systems, or you could actually use it for future code design, right? As you're designing a new system, completely new, or some technology part isn't in physical form yet, you need to do some simulations to actually vet, system 1 versus system 2. So you would be able to do that kind of stuff with some open source tools. And then there's a lot of, I would say, more commercial, or even some, operators, internal tooling that they actually build off of this as downstream tool that they actually run internally to actually do similar things, right, as you have in the open source ecosystem. So now, to walk you through all of the technical details, I'll pass it off to Dan.
Thanks, Winston. So let me show you how Chakra execution trace looks like. This diagram shows how distributed neural network training gets represented. The original deep neural network model gets captured as execution patterns across multiple GPUs. Here, orange, green, blue, and yellow circles are compute operations, like forward pass, weight gradients, input gradients computations. Red circles represent communication operations like or reduce. We can capture arbitrary distributed workloads and any parallelization strategies, being data parallel, model parallel, pipeline parallel, or other hybrid approaches. These can be collected from real systems or can be synthetically generated, giving you the flexibility to start with current production and then explore what-if scenarios for future systems. So here is more detail. Chakra uses an extensible graph format. Nodes represent the primitive operators and the tensor objects with attributes and timing assigned into them, captured into them. The edges represent the data and the control dependencies between the nodes. In the graph at the right, the tensor objects are in green with dependencies that are connecting communications operations with blue and compute operations with orange. The operations can execute concurrently once the dependencies are once the dependencies are satisfied. The key benefits of this are that we are able to isolate communications and the compute operations to capture timing in order to replay and simulate later, to represent both the workloads and the collective implementations using this format, and if needed, to apply graph transformations to protect intellectual property while preserving the performance characteristics of the workload. So here's the actual protobuf schema that's at the core of the Chakra execution trace. It is very simple on purpose. It has only 5 required fields: an ID, a name, a type, and control and data dependencies. The node type can be compute nodes, memory operations, and 3 types of communication nodes: send, receive, and collective. As I mentioned, the design is minimal on purpose and it's extensible. Everything else can go into the attribute proto fields that support all the known data types, standard data types. Other people can add, users can add metadata without breaking compatibility, MPI collective implementation details, all these as attributes while maintaining the interoperability. So the trace collection is the critical first step. We support collection from production AI workloads with a minimum overhead. Collection happens during the normal operation. There is no need to run special benchmarks separately. Certain hyperscalers have deployed this across their entire training fleet. You can get traces at different abstraction levels. And the Chakra converter and synthesizer produce representative obfuscated traces for current system, to be used for current system benchmarking, future system co-design, and or open source simulation and emulation. Here's the detailed PyTorch implementation. As you can see, there are minimal code modifications. Just enable the execution graph observer object. And then we are able to collect PyTorch host traces and Kineto device traces from the GPU. The trace merger tool links PyTorch ops with Kineto ops. At the same time, encoding durations and other metadata. The Chakra converter produces standardized format for the simulators or the emulators to run. So there is minimal overhead, non-intrusive changes, and produce high fidelity traces. Here are a couple of examples of actual Chakra traces. The left side shows a very simple dependency graph, which has been synthetically generated. The right one is a complex real-world trace captured from a real-world workload with the full dependency structure. This captures the actual execution behavior of the distributed AI workload. There's precise operation sequences, dependencies between them, and timing from the real production system from which it has been collected from. The first major use case is the replay benchmarking, which enables production teams to quickly reproduce bugs, run performance regressions, or run benchmarks on real systems. For example, the Mystic system presented at ISCA 2023 showed an automated infrastructure for production fleet benchmarking. We also support commercial emulators like Keysight's AI data center builder for pre-production validation. The key value here is agility, being able to replay exact execution patterns without needing to reconstruct the complex workloads from scratch. The second use case that I'm going to talk about is the simulation and emulation use case for future systems co-design. Here, the goal is to execute workloads and project performance on future systems. The component here is part of the ecosystem is the execution trace feeder, which is a C++ library that provides a clean interface for the simulator. It works with the Astra Sim open source simulator and proprietary emulators. This enables modeling of different network topologies, node configurations, and collective implementations to see and experiment the impact on real workload before hardware, even before hardware availability. The Chakra ecosystem consists of several comprehensive supporting tools. A couple of examples are the execution trace visualizer, which generates dependency graphs in various formats, and the timeline visualizer, which integrates with Chrome tracing for to be able to visualize execution timelines. These tools are crucial for understanding distributed performance, see exactly where communication blocks computation, where load imbalances occur, where optimization opportunities exist. All are open source tools that can be integrated into existing workflows. So the key takeaways is that Chakra execution trace is an open graph-based representation that enables isolation and optimization of compute, memory, and communication behavior. It is a complete ecosystem that can be used for benchmarking, for performance analysis, and performance projection. All resources are available online. There's a GitHub repository, a wiki, and the original concept paper. Participation is open through registration through ML Commons, through the ML Commons working group. There are bi-weekly meetings on Monday at 11 a.m. Pacific time. So the bottom line is that we believe that Chakra represents the future of AI and high-performance computing performance analysis. It's a vendor neutral and directly applicable to distributed performance challenges investigations. Early adoptions gives you influence over the standard development with clear applicability in the AI and HPC optimization. Thank you.
We have time for a few questions.
Yeah, I do have a question. So currently there are some fusion kernel in the AI workload, like fused computation and the communication, just like DeepSeek, DeepEP, those kernel, like whether Chakra have the ability to like considering those fused kernel, yeah.
So that's a great question. And that's actually one of the node types we're actually thinking about extending in the protobuf schema. So if you're interested, come and then we could participate and you could help us to actually drive it too. Yeah.
Any other questions?
So,
Yes.
a question was like, if I wanted to go look at Llama 4, right, which would be inline because of the people involved, what would it take for me to generate a Chakra execution trace? Like, can I just say, hey, run a Llama 4 training load and generate a trace? What does it take?
So you want to do it?
Yeah,
or?
I can say.
Okay.
So there are the PyTorch code needs to be instrumented. As I mentioned, there's an observer. the impact on performance would be minimal. So just need to run. You have to instrument the PyTorch code, and just need to run it, get the trace, combine it with the Kineto trace, and we obtain the
Yeah.
trace.
So I think the other thing is like, so if somebody has a concept on what that sort of neural network architecture is, right? And if you implement it in PyTorch, one way is do the, the observer stuff. But, I think there's people thinking about also, there's a way that you could probably look at even the code itself and be able to extract the dependencies without necessarily even running it, right? And then be able to get you a sketch of the trace, right? Not necessarily the exact 100% code. So theoretically, it's like if you have a sketch of what the thing, 80% to the semblance of what you want, and then if you're thinking about the overall system design, A versus B, it would give you a relative merits of the two systems that you're testing it against.
But you would
right?
have to do that at the IR level, right? You wouldn't, especially for compile, you would need to run it against the IR. So I think, okay, maybe you don't need to run it on PyTorch, the execution runtime, but you will have to, unless you want to embed all that logic into
Yeah.
Chakra itself.
So I'm saying like some things you would have to, how do you say it? Like, I think there's way that you could run it before the whole model is actually sort of completely trained and you have all the code, right? Which will get you to a certain level, but eventually when you have that model, then yeah, you have to put in a few decorators, spit out certain operations, and then give you the trace, then yeah.
I think Nauras, you had a question? Yeah.
Yeah, a quick one. So that when you mentioned that observer, does it basically just look at the CUDA stream and see what sort of kernels are launched, and that's how the graph is generated at this point, or
It's a PyTorch. It's a
PyTorch level? Okay. So, and like how would this differ than like existing tools like CUDA graph, for example? So what would Chakra show me that a CUDA graph would not be able to capture? Or is, yeah.
I'm not aware of that CUDA tool you're mentioning, but what I could say is that this can capture all types of operations, meaning communications, compute, and memory operations.
Okay.
I mean, and I think if you go back to the previous slide, right? Like, I'll just add on to that a little, right? So really, like, if you look at it at the top, right below PyTorch, right? You do have the observer stuff that's coming out of PyTorch itself, but there's also the Kineto trace, which has piece of the puzzle, right? So you kind of have to combine the two together in order to get you the Chakra thing that's useful for, the more cohesive view. So
Yeah, that makes sense. Thank you.
I have a question, like you indicate, like you are trying to do also performance projection, like based on your Chakra and then the traces. How accurate you have seen? Are you able to project with a very 100% accuracy or some range?
It depends. So in order to project accuracy, you would, for example, either use a simulator or an emulator. So emulator would mean running on a physical system, which would probably be more accurate, but for, let's say, more earlier stages of pre-production, running it through a simulator, I guess it would be as accurate as the simulator underneath it is.
And I'll add on to that is that I think, the dependencies in terms of tracking the orders of these operations, right? It's pretty accurate, but I think the key thing is sort of like, how do you know that what you capture on one system,
Yes.
you play it back, and that's the thing where like, like I've seen people actually been trying to characterize the individual operations right? The A10 operators, like individually on certain systems, and then project out based on, it's more, based on sort of like just the raw sort of power of the GPU and stuff, right? And then kind of like analytically sort of extrapolate. But ultimately, I think it's the way we look at it, like we've seen people use it is, you have some simulation stuff, get you the rough design. Once you start doing the hardware prototyping, some of the early prototypes come back in FPGAs or whatever, like you run it again. You kind of study it at smaller scale, right? And then see like, is it really off from your simulations? And you have to kind of calibrate and potentially update your simulations and vice versa. There's a calibration step in at some point in time, right? If you want to then, so for example, because for us, right, like some of our customers take this and then run it in pre-production lab with the test equipment, but they're not going to build out like say, 10K clusters with test equipment. So they would run it to certain size, calibrate it, and then they'll actually then, go back to simulation and run it at that higher size. Right. So,
Any other questions? Are there any remote questions? Okay, so let's give thanks to both Winston and Dan. So before we go into the open mic session, we have 2 short talks by the students. As I was telling